Hello and welcome to Australia in Space TV. My name's Chris Cubbage. I'm the editor with My Security Media and Australia in Space TV. Today we're joined from Curtin University here in Perth, Dr. Hadrien Devillepoix and Professor Fred Jourdan. Gents, thanks for joining us.
Thanks for having us.
Yeah, thanks.
Wonderful. Now, this is a 2.2% chance of an asteroid hitting Earth, and it's been tracked. And it's called 2024 YR4. It's been tracked since December. And it's obviously, I understand it's moving away from Earth as well, which is causing some issues. But Hadrien, maybe talk us through this particular asteroid and how it's been tracked. And then we'll move into sort of the risk it may well pose. It's not a planetary existential threat, but it may well sort of come close to us.
Yeah, it's definitely one we need to keep an eye on. So the way we've been tracking this asteroid, I guess, since just before Christmas, it was kind of formally discovered just after Christmas, is basically taking telescope images of the asteroid. So the asteroid is reflecting sunlight, is basically appearing almost as a star. It's like a moving star in our images. So we take pictures through telescopes that need to get bigger and bigger because the asteroid is moving away from us and therefore it's reflecting less sunlight, or less sunlight is getting to us. But the main technique for tracking this asteroid is it's normal pictures. Some people would have taken pictures with their phones of the stars, like holding still, long exposures with their cameras, or more either phones or like cameras and lenses. It's the same principle, just like much bigger telescope collecting a lot more light to get to these faint objects.
One of the thoughts I had is because we're losing the ability to track it. I would have thought we can point anything to these and start to track them, and even start to move some of the other telescopes around and the like, particularly when it is a threat. Why is it such a challenge at the moment?
So at the moment, the asteroid is moving like away from us fast. So usually when we're talking about asteroid speeds, we're talking kilometers per second. We're talking like usually something around 10 to 20 kilometers per second. So, and then that thing is moving away. So currently we need a roughly kind of 2 meter class telescope, so we can have 2 meter across mirror. In 2 months' time, we'll need like an 8 meter class. It's not many in the world that can do that. And we might be able to track it until May with the telescopes like the James Webb Space Telescope or the Hubble Space Telescope. But after that, it'll be gone. It'll be basically invisible for us for at least 4 years until it gets close again to the Earth in 2028.
And given the uncertainty on the percentage as to, obviously we haven't had enough accurate data to project its current orbit.
Yeah, absolutely. So the way you have to think about these things, like think somebody's just kicked a ball or hit like a tennis ball, and all you're looking at of the trajectory of that ball is the very beginning. Like the ball's just left the racket, it's just been kicked. Imagine you looking at the trajectory of that object and you just got that little glimpse of what's happening at the beginning. How well can you predict where that ball is going to land later on? Not very well. So that's the problem we've got at the moment is, we're taking plenty of images, but we really need to cover a longer arc of the trajectory to get a better feel for where it is going, what its orbit is, and therefore what the chances are for impacting.
Well, the trigger here was it jumped from a 1% chance to a 2.2. I know that's only a 1% change, but it's also 100% increase in the percentage. Obviously they're projecting it forward, and it's looking like it may well come close. Even with that 98%, how close is this likely to come? Are we going to see it in the night sky kind of thing?
So this one I think will be too small to be naked eye visible when it comes like quite close in 2032. So hopefully it'll just be quite close and not actually impacting. Sorry, I missed the beginning of your question.
How close will it come? Will we be able to see it in the night sky?
No, I don't think we'll be able to see it, just because it's like such a small asteroid. You'll need at least some sort of telescope or perhaps binoculars. I haven't checked exactly how bright it will be.
Well, I suppose that's the advantage here. It is quite small, so the potential impacts, and maybe Fred, just some of the work that you do in this area as well, but just in the likelihood that this could actually hit. As I mentioned, it's not an existential threat, but it could, depends on where it goes, most likely in the ocean, we would hope. Is there any sort of modelling? Do we have an understanding of something this size? I think it was between 40 to 90 metres wide. Just have an understanding of what is likely to happen if it does hit, or something similar into the future happens?
Well, I mean, that's not that big indeed. 90 meter is fairly small, but it depends which perspective you have. If it falls on your city, if it falls on Perth, all right, and well, everybody's dead pretty much, or at least, like half the population. But we would know it, so we would evacuate. But that just
Yeah.
still gonna wreck the city completely. But that's what we're talking about. It's a city killer. It's not like a species killer or continent killer or anything like that. So that will leave a crater which would be like 1-2 kilometer wide. Think about the crater in Arizona, meteor crater, Barringer they call it now,
Yeah.
and that would be that size, but that would be almost as powerful as the most powerful nuclear bomb we ever detonated. Not quite, I mean, according to the model, but if you think about that's still a lot of energy, right? Now, that being said, 70% or more of the Earth is covered by water. And even on the land, most of it is not really inhabited. I mean, I think like there's 2-3% covered by city. So you get this tiny 2% chance. And then you get only 2% chance it fall on the city. So that's really a small percentage that it's going to really devastate anything. But still, if it's your city, then you start to care, So
It
that's
sounds
the
like
thing.
it's enough chance of getting hit by lightning than it is by an asteroid. But I suppose the other aspect is if it hits in the water, which is most likely given those percentages, I take it that could have more of a damaging impact, some sort of tsunami or something like that. Is that
Now,
likely?
No, no. I mean, unless it's really close to the coast. Well, of course,
Yeah.
if it's 5 kilometers to the coast, I mean, you can neglect the water. It's almost an impact on ground, and the water is really pushed very quickly. So that would be a big tsunami. But if it falls in the middle of the ocean, well, no, because
As long as it's deep.
earthquake, they just move the ground, so there's a lot of water displaced. But this is an explosion in water.
Yeah.
Think about all the tests that we did with nuclear bomb, in the ocean, and there's not that much tsunami that went around, hopefully, because otherwise people would have been really pissed off if it was the case. No, it wasn't. So that's the same. That's an explosion like a nuclear bomb.
So go. Sorry, Hadrien.
I
Go.
was going to say, what if it's okay in the unlikely event that it's still going to hit the Earth, even after we get more observations, and if we know it's going to hit like over the ocean, as Fred is saying, there's not much risk. As a meteor scientist, I'd probably actually like to see impact. So last time we had, an impact that big around the kind of what we call like megaton of TNT equivalent class impact was the Tunguska in Russia in June 1908. And that happened over like fairly unpopulated places. It did, I think, by some accounts, kill about 3 people and knock down 80 million trees. So it was kind of local devastation of that.
Was that a similar size?
It was similar size. So there's still a lot of uncertainty about what the size of the object is, and I guess therefore what the kinetic energy released in the atmosphere would be. But we're talking about kind of similar order of magnitude. And that, back in 1908, we didn't have many instruments looking at this. We had a couple of eyewitnesses, obviously what that did to the forest, and a couple of seismometers around the world that picked it up. But if we were able to study this thing and we knew it was going to impact somewhere that's pretty safe, that'd be a pretty good opportunity for science as well.
Well, I had 2 questions out of that. One is, what type of information do we have on that? And how much warning did they have, or was that just suddenly came out of the sky with no warning whatsoever? So I imagine that would have been quite a shock. But also the data that what might have been well collected. The other one is, this sounds like a 1.5 century risk that Earth faces if that's the case. On that point, how common is this really? You hear this quite more frequently, I suppose, in the news. that they are aware of asteroids, and now we're landing on them. We're moving, we're bringing it back samples as well. So they're not a rare phenomenon. But yeah, just how many, this is an ongoing thing that we just need to be aware of. And the more scenario planning that we do, the better we'll be.
Yeah, I mean, the big thing that's changed since 100 years is like we now are able to have the tools, the telescopes, basically looking out for those objects to detect them. So that's why we know about them. So the Tunguska impact in 1909, like nobody saw that one coming because we didn't have the tools. The ones that killed the dinosaurs, though, that led to the extinction of like a lot of the dinosaurs 66 million years ago, was a 10-kilometer asteroid. That one would have been a bright spot in the sky for quite a while.
Yeah.
If dinosaurs knew what to make of that information.
They must have seen something coming. I'm sure they were sending out some noises, asking themselves what that was about to hit them. But I suppose that's the point here, isn't it? The amount of small asteroids that are flying around space versus those big ones. Are we aware of any big ones, even if they're not coming close?
Yeah, so I don't know if you've heard of the Apophis asteroid. So that one was discovered in 2004, and it is like 300 to 400 meters across. And early on, there was a relatively high probability, considering how big the asteroid is, of an impact in 2036. So for 2 years, we did not know, we could not fully rule out an impact in 2036 for that big asteroid. And the cool thing with that one is actually going to come really close to the Earth in 2029, I think in April. And that one will be naked eye visible. So we know it's not going to impact neither in 2029, neither in 2036, but it will be naked eye visible, and people will be able to see it, which is quite exciting. But it also teaches us a lesson about sometimes how patient we have to be to get more observations of these things. Like for Apophis, which would have been a really big deal if it wasn't collision course, we had to wait 2-4 years to get enough observations to characterize its orbit well enough.
Well, the other thing in the notes that I've got from your team is the potential to move this and the like, and it has been shown that we can change the trajectory of asteroids. This doesn't sound like it's worth doing, but yeah, Fred, just your thoughts on that and the capabilities here. Obviously, it's been thought about and tested.
Yeah. With the DART mission, they did a really good job. I think the asteroid they moved, there was a mini moon, Dimorphos, around the asteroid Didymos. And the mini moon was 160 meter wide, so a bit bigger than this one. And they managed to move it a tiny bit of its orbit. But that's the thing. They managed to move it a tiny bit from its orbit. So people need to keep that in mind, that this approach, that smashing probe into asteroid, it's not like, oh, okay, well, we know how to do it, it's safe. No, it takes a lot of time. So many probe to start to move the thing a tiny bit each notch. But when you don't have that much time, then it's a different story. I mean, how do you do that? It's like, okay, next passage is going to be in 4-year time, and then we do calculations like, oh, it's 95% chance it's going to smack on purse again. I always use purse, but like, because it's really dear to my heart. So then in this case, we want to do something, and I'm sure everybody is organized themselves to do something about it. But like just sending a probe and we get like 4 years and less, because we need to send a probe when it comes back from the orbit, we get even less time. We won't push it out. So what can we do? And one of the answer of that is like looking at the structure of the asteroid, because depending the structure, you can do different stuff. Now, some work we did on asteroid Itokawa was to show that those rubble pile type of asteroid, so the one made of loosely bound rubble, they're particularly good at resisting impact and an explosion. So if you try to do an explosion near a solid chunk of asteroid, there's a lot of chance that it's going to fragment and explode. So instead of destroying Perth, it's going to rain on Beijing, Washington, and Perth. And everybody is going to be pissed off at Australian people.
At least we share it around.
Yeah, well, yeah, you can see it like that. Like, hey, scientists, right? We share with you. But no, so it could cause big drama, actually, to do something like that. But if it's a rubble pile asteroid, it's resistant to that. So if you detonate a bomb beside, and a big nuclear bomb, then you could push it away without destroying, but a good push, not like just those tiny nudge. So that's something worth exploring. But of course, there's a lot of legislation about what you can do in space, nuclear device in space, which are a bit interesting because space is so big. It's not like you're going to pollute anything with radiation. I mean, there's radiation everywhere in space, but in space. But it's more about proliferation of nuclear device and people being, oh well, why are you making this device? Is that ready for helping in space, or this kind of thing?
Well, it gets me thinking about even the space debris. We've got a lot of assets out in space, in orbit, and so it may not have to hit Earth. It just needs to come close enough to start to threaten things like our space debris. Anything like that, is that in consideration as well, Hadrien? I suppose we can still move most of these assets around, but we do have space junk flying around that could well get close enough.
Yeah, well, I think as long as no humans up there or that are in danger of getting hit, at the end of the day, it's just hardware. It's expensive hardware, but just hardware.
Fair enough.
At the moment, to give you an idea, it's like how little we know about that encounters. Like we don't know if it's going to hit the Earth, or we don't know if it's going to just safely pass us beyond the moon. So yeah, lots of uncertainty here. If it safely passes beyond the moon, it's not going to hit anything man-made.
Well, I did have a question on that. We are sending missions to the moon and Mars. Are we tracking what's hitting those bodies as well, or are we only just focused on Earth? Is there current research that you're aware of for tracking what's hitting the moon and Mars?
So not aware of research or missions looking at what's hitting Mars. We've got some models, but not really direct observations. I am part of a mission called the LUMIO mission, so it's led by the European Space Agency, and that one's going to look at meteoroid impacts on the far side of the moon to try to characterize what's happening at the moon. Why is it different from Earth? Like, what's the comparison? So yeah, basically looking at the entire dark side of the moon, which is quite exciting, and that will fly hopefully in 2027.
Nice. That sounds like a good one. We'll definitely keep current with that one. And I suppose just to finish off, gents, Fred, you are with the School of Earth and Planetary Sciences at Edith Cowan University. And Hadrien, you're the lead scientist in the Desert Fireball Network with Curtin University. Maybe day to day, what are you currently focused on, Fred?
Currently working on the samples from Asteroid Bennu. So that's funny. You mentioned that before, like the asteroid that can smack on us. One of the goal of the mission was really to understand Bennu better, because there's a chance that a small chance, even smaller than the 1% we're talking about, but it impacts us in 2,100 something. And so NASA want to understand this big asteroid, which is again 500 meter wide, because that would cause more devastation. It's a bit exponential when things like that impact. So it's not like 5 times more powerful; it's many more times powerful. So by understanding the structure of this asteroid, the composition and things, it's much easier to come up with a plan, especially in the far future like that. Where technology is going to improve. To deflect those asteroids. But what we're interested in my team is not so much about deflecting this asteroid. It's more about understanding the origin of the solar system, how things form at the beginning, how rubble pile asteroids form, all those blue sky science questions that we're trying to answer. And we were fortunate enough to be part of this mission. So among the first labs in the world to receive some sample directly from NASA. And that's a pretty cool mission. I really like
Very good. It's good to have that samples here in Perth as well. And Hadrien, the Desert Fireball Network, aptly called, given we're talking about asteroids hitting Earth. The Desert Fireball Network.
Yeah, so the main goal of our main mission is to observe fireballs made from kind of like small asteroids. We're talking kind of 10 centimeters to maybe meter across. Observe them like crashing into our atmosphere as big fireballs, and try to get meteorites from them, and then linking basically those like small asteroids, where they came from, what orbit they came from, with the types of geochemical analysis that Fred can do in his lab. Linking that together tells stories about the solar system. But the thing I'm really excited about is at the end of the year, there's the Vera Rubin Observatory starting, which is a big 8-meter telescope. That's going to be finding lots of asteroids, definitely. But a particular class of asteroids is going to be what we call imminent impactors. And those will be typically meter cross size asteroids that we'll see come in, and we'll have just a couple of hours warning that this one is going to impact, safely going to impact, because they'll be small. But us knowing about these things in advance will be really exciting, because we will tell people, hey, go out there and look up, because you're about to see a show of your life, and we're really excited about that. It'll be very exciting for science studies as well.
Well, I'm thinking of and being able to model that as well, and just being create a sort of a virtual sort of model of how that happens as well would be fascinating. Look, gents, I've got a million other questions I could talk to you all afternoon. Fascinating area. It's great to have you both representing Curtin University, who is our national partner as well. So we will definitely be tracking what Curtin University is doing across the space domain. And this in particular from the School of Earth and Planetary Sciences is fascinating. So Professor Fred Jourdan and Dr. Hadrien Devillepoix, I've got to practice my French. Thank you very much for joining us today on Australia in Space TV.
Cool. Thanks for having us.
Thank you.